Alright, welcome back, ladies and gentlemen. We're talking about logarithmic functions now. We're going to be converting equations between log and exponential forms, evaluating log functions, and solving log equations. Okay, I'm working off the idea that you have a basic memory of logs. So here we go. Okay, any function in the form f of x equals log base a of x is a logarithmic function, and a few conditions on there. A can't be equal to 1, so the base right here can't be 1. Because honestly then it makes it very boring, kind of like with the exponentials. A's got to be greater than 0, so I can't take log base negative something or other. And also x has got to be greater than 0, so I can't take the log of a negative number or even 0. Alright, so there's the basic conditions on that, and as we go through this, maybe that'll make a little more sense in case it doesn't already. Alright, moving along, the equations y equals log base a of x and x equals a to the y are equivalent. And that's going to allow us to convert between log and exponential form because honestly sometimes one is better than the other depending on what you're doing. Okay, now notice that log, okay, well, I've got y equals this logarithmic statement right here, this function, whatever you want to call it, expression. Okay, well, y is that log thing. Well, notice the other form of this thing, okay, y is an exponent, and y is equal to the log, and y is an exponent, so hey, log is actually an exponent. So whenever we're talking about logarithm, we're really talking about exponents. So as we talk about the rules and the properties and stuff later, okay, any log property is really derived from an exponent property. Okay, additionally, log functions, because of the way we manipulate those two equations around to make them equal to each other, log functions are actually inverses of exponential functions. And I'll admit I won't make too much use of that today, but as we move forward, and hopefully it's going to make a little more sense. Alright, and so that's the basics. Let's move on to the more interesting stuff. Okay, something we need to take care of as we talk about logs is some implied numbers and things of that nature. Okay, if no base is written with a log, okay, it is understood to be base 10. Okay, so as soon as I write log x equals y, again, notice there's no little subscript right there. Okay, that really means log base 10 of x equals y. So one of those few times in math where if there's no number there, it's something other than a 1. We've had a couple of those, and this is another one. Okay, and this is known as the common log. Alright, so whenever we hear common log, that's what we're talking about. Okay, now if base of the log is e, you write it as, it's ln. I know it looks like it might be a 1n or something like that, but it's an ln. For whatever reason in the calculator, or at least some calculators, they actually use a capital L, capital N for this. I have no idea why, but that's how it works. So if you don't see the ln button with lowercase, look for a capital letter one, and that's going to be the one that works for you. Okay, so anyway, log base e of b equals x is actually something you're never going to see as at least a final answer or something like that. So basically this is an incorrect equation because of the format. It should be correctly written as ln b equals x. Okay, so again, the log base e turns into an ln, and it's understood to be a little base e right there, and this is known as the natural log. Okay, now hopefully that makes a little more sense why you have ln, although you might think it's supposed to be nl, but I think it was originally made up by a French mathematician, and in France the verbs, the nouns and the adjectives usually go in a different order, so that's why it's the log naturel as opposed to the natural log. But just in case you were curious, there it is. Okay, now sometimes it's going to be important for us to convert between log versus exponential form because honestly sometimes one is going to be more convenient than the other depending on what we're trying to do. Alright, so we want to rewrite in the other form. Okay, and again, I know you've seen this before, so I'll hopefully go through this fairly quickly and not bore you to death. But log base n of 7 equals 4. If you look back at that basic format from the couple of slides ago, basically this can translate into n to the 4th equals 7. I'm not asking you to solve any equation or anything right now, so basically this is all I'm looking for. Just rewrite the equation in the other format. I just kind of visually think that the low number goes to that power on the other side of the equal sign, and then it equals the guy inside. So I kind of like just mentally have that go there, and then I throw that on the other side of the equal sign. I don't know if that makes sense to you. For some reason in my brain it makes sense. Okay, that being said, if I'm looking at this, okay, log w equals x, now remember, since there's no number there as a subscript, it's really a 10, so this guy becomes 10 to the x equals w. Okay, so same thing, that number goes to that power and equals the thing inside the log, if you will. Okay, same thing over here, ln y, well, for a natural log of y is, again, understood, little subscript e is the base. So similarly to the last one, it actually ends up e to the d power equals y. Okay, going the other way, and I'll admit it's a little more awkward going this way into the log form because honestly our brains just like exponents better than logs. So here we go. Okay, so I know I'm going to have log form, so I'm going to write the word log because I'm going to get started that way. Okay, although notice that the subscript here is the base, and basically what that is, the base of the log is the base of the exponent, so that works out very nicely, at least I think so. So the 5 right here is the base, so I'm going to put that there. And then remember, log is an exponent, so the thing on the other side of the equal sign should be the exponent, so in this case it's the 4. And kind of by process of elimination, that means the 625 is right there. Try to squeeze that in. Okay, and again, just to kind of check it going the other way, 5 to the 4th equals 625. Oh yeah, it works. I feel good about life in general. There you go. Okay, so we can do this the other way. Notice the e, okay, and again, it is the base, so that lets me know that I'm going to have a log base e, and again, if you write log base e, I will not be overly pleased, so please write ln for that. Alright, and then again, the exponent is the thing on the other side of the equal sign, so I know that 3 is going to go there, and then again, process of elimination, I know that r is going to go inside the log, if you will. So natural log of r equals 3. Okay, and here I'm trying to mess with you, I put things on the other side, and if you ever see that, well, you know, just foil my cunning plan by just rewriting it the other way, and then hopefully it makes a little more sense this way. So again, okay, I'm going to have a log, and the base of the log is 10, so hey, I don't have to write that. Okay, the exponent goes on the other side, and then again, process elimination, there you go. So you got log e equals x. Doesn't that sound cute that way? But anyway, log y equals x. Hopefully that makes a little bit of sense. Alright, now if we're evaluating logs, remember evaluating basically means you're finding a number. Okay, so anytime you're talking about evaluating something, you should eventually get to a single number as your final answer. Alright, so what we can do here, basically I'm asking, because log is an exponent, I'm asking what exponent takes me from 4 to 16. Okay, now hopefully that's pretty obviously going to be 2 for us. But just to show my process here, because I'm going to use it on some nastier stuff in a second, I'm just going to imagine this thing is equal to x. Okay, and then I'm going to rewrite this thing into the exponential form because my brain just likes that better. So this becomes 4 to the x equals 16. Alright, and then again, if I want to use my duh property, this becomes 4 to the x equals, well, say 16 is 4 squared. So very quickly, x equals 2. But notice this x is something that I manufactured just for this problem. It wasn't part of the original. So the final answer I'm looking for here is actually just the 2 and not saying x equals 2 because, again, there was no x to start with. It's something I made up. Okay, so at least that's a process you can go by to do this in case the number isn't obvious enough just looking at the numbers you have. Okay, here, log of 100,000. Well, again, since there's no number there, it's really a 10, and again, if it helps you, think of that as equal to x. So this is 10 to the x equals 10,000. Okay, and hopefully you're good at powers of 10, but it's pretty simple, because if how many zeros you have is what exponent you have on the 10. So 10 to the x equals 10 to the 5th, and again, the x is something I manufactured, so really what this thing is equal to is the 5. Alright, moving on to this next one, log base 7 of 1. Okay, now that one might seem a little weird, so let's just kind of take a look at this one using the x again. Hopefully you already know the answer, but in case not, here it is. Okay, we got 7 to the x equals 1. Okay, now you might be thinking, huh? I don't know what's going on there. Life doesn't make sense anymore. Well, okay, well, let's see. I got to take 7 to some power and get 1 as an answer. Well, if you remember, 7 to some power, well, let's see, 1, 7 to the, oh yeah, 0 power. Okay, basically, so what you have to kind of keep in the back of your mind is anytime you see a 1 right there, think, hey, maybe that's something to the 0 power, and in this case, it certainly is, so 0. So again, 7 to the 0 power equals 1, so it does check out. Okay, now here, the gut reaction of a lot of people is, oh, 2, and unfortunately, you would be wrong. Alright, so again, I'm thinking this is going to equal x, so I've got 9 to the x equals 3. Okay, now notice again, if your gut reaction was 2 right there, you're telling me that 81 and 3 are the same thing. And last time I checked, that's not quite true. So I need to figure out something to do, and let's replace that 9 with a 3 squared, and that's going to be equal to 3 to the first. So ultimately I have 3 to the 2x equals 3 to the first, and hopefully without too much effort there, and mostly I'm running out of room here, hopefully that gets you x equals 1/2, or again, really I don't even want the x part of my answer, so that's 1/2. Okay, now remember 1/2 is the same thing as saying a square root. So that's all this is saying here. What root of 9, or what power of 9 gets you to 3, and it's the 1/2 power because I have to think of it as a square root. So again, basically all I'm saying there is, hey, because this is true, I know that exponent has to be a 1/2 to take me from 9 to 3. Okay, now I hope that your brain isn't oozing out of your ears yet, because it's about to get worse. Alright, so we've got these three guys here. Okay, 8 to some power has got to give me 1/64. Well, hopefully the second you see that, you start thinking, hey, wait a minute, I got a fraction here. The only way to pull off a fraction using exponents is to have a negative exponent. So as I think about this thing being equal to x, kind of as foreshadowing, if you will, I know I'm going to have a negative answer. So again, kind of just running through my steps here. 8 to the x, again, my manufactured x that doesn't really mean anything for this problem, equals 1/64. Okay, well, so 8 to the x, see, 1/64, well, that's 1/8 squared, and I really wouldn't expect you to do that step. I would more expect you to go straight to 8 to the -2, and then kind of the dove property takes over, x equals -2, but again, I'm going to ignore my manufactured x, and just say -2 is my answer, so 8 to the -2 equals 1/64. Now granted, those steps may or may not be necessary, depending on your particular skill on the mental math field right there. Alright, similarly here, I've got log base 125 equals 1/5, and again, your brain may want to go on strike right now, and if that's the case, set up an equation. So 125 to the x equals 1/5. Alright, so now I've got kind of a mixed bag of stuff here, but hopefully you can look at that and think, oh, I got a common base of 5. So again, now 5 to the 3rd, and that's all being risen to the x power, equals, let's see, to pull off the 1/5, that's got to be 5 to the -1. Okay, cleaning up the mess on the left-hand side gives me 5 to the 3x, and that equals 5 to the -1. Alright, so again, dividing by my 3, and then ignoring the fact that I have a made-up x in that problem, I get -1/3. Okay, the negative flipped me upside down, and then the 1/3 is again effectively a root, so the 3rd root of 125 takes me down to 5. So hopefully that makes sense. The negative means I had to flip it, and the fact that I have a fraction means that I had to take a root to get from this bigger number down to this smaller number. Okay, lastly we've got this thing, and again you might be thinking OMG, but again, if we think of an x over there, it kind of plays itself out pretty nicely. 27 to the x equals 81. Okay, and again, playing around mentally with this after a little while, hopefully you stumble on the fact that 3 to various powers takes me to both of these numbers. So I've got 3 to the 3rd to the x has got to be 3 to the 4th. Alright, so again, a little bit of cleanup gives me 3 to the 3x equals 3 to the 4th. With my dove property working and a little bit of division, I get 4/3. Okay, and hopefully in the back of your mind someplace, remember that the denominator is a root and the top number is a power. So again, if you can look at that 27 and think, hey, if I take a 3rd root, ding 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 ding, that takes me down to a 3, and then 3 to get up to the 81 is the 4th power. So whatever bottom number is the root you need to take to get down to some common base, and then the numerator is going to be whatever power it takes to get from that common base up to the other number right there. So just a few things you can keep in mind as you do these kind of things. And again, setting up the equation is great. If you don't need to set up the equation, that's going to make me want to give you a big just hug. But of course, use the equation if you need to. Alright, now there's some inverse properties that go along with logs. Now I mentioned the inverses for exponents and logs earlier, and I'm not exactly talking about those, although they are kind of related. Alright, now these properties, I'll admit, will not be used a ton, but every now and then they do pop up and are kind of handy to have in your back pocket in case you need them. Okay, so again, log base 404 to the x. Okay, now there's some commonality there, of course, between the base and the number inside the log, so that's probably a hint as to what might happen. But again, if it's not obvious, let's, and I can't set it equal to x because I already have an x there, so I'm going to set it equal to question mark, just because that's just crazy looking. Alright, so now I'm going to turn this thing into an exponential form, and from the log form. So the base goes to the power on the other side, so 4 to the question mark power, okay, very fancy math notation there, I assure you, equals the thing inside the log, which is 4 to the x. Okay, so with my duh property at work, that lets me know that that question mark is actually equal to x. Okay, so this logarithmic statement, expression, whatever, is actually equal to just x, which notices just this exponent right there. So basically, the moral of the story is that if the two numbers match here between the base of the log and the number inside the log, regardless of the exponent, it's going to be equal to whatever that exponent is. Okay, that being said, if we look at the second example, natural log of e to the x plus 4, again, keep in mind that natural log e has got a base, which is a subscript of e down there. And so basically the two e's cancel along with the natural log and give you a final answer of x plus 4. Alright, this set of thing, this one's a little less often used than the first property, where those guys cancel out and leave you with the exponent as the final answer. Okay, again, this is equal to something, and I'm not really sure what it is, so I'm just going to set it equal to question mark and see how this guy plays out. Okay, now, it may not be obvious, but this is actually an exponential form right here. Okay, because I have a number to a power equals something else. Okay, so I'm going to convert this into log form. Alright, now brace yourself, this gets a little crazy. Okay, so I'm going to take the natural log, and I'm doing that because that's what the base I have. So I'm going to put that little subscript e just to kind of show where the base comes from. Okay, so natural log, which again is base e, of the thing on the other side, which is a question mark, is going to equal to the exponent. Guys, remember, a log is equal to an exponent, so in this case an exponent is ln 3. And again, the little subscripts there, if that helps see what's going on here. So I've got log of something equals log of something else. Well, duh, that must mean that the question mark, whatever that thingy is equal to 3. So again, notice that this base matches the base of that log, which is an exponent, which is kind of crazy to see, is equal to that question mark, and that question mark is equal to 3. So basically the e with the log cancel each other out, and just leaves you with a 3. Okay, again, not often used, but there it is. And so now if I'm looking at this other guy, because that log without a base written in there is really base 10, that whole thing cancels out, and the final answer is just a plain old ordinary 6. Alright, so again, the top two you're going to see a little bit more often, in fact a lot more often than the bottom two, but it's just one of those things. Keep in your bag of tricks, because every now and then it shows up and is handy to have. Alright, now solving equations. Admittedly, we're going to have some fairly basic equations now. They're going to get worse as we move on to more complicated stuff, but for now, let's just take a look at these two real quickly. Okay, well, log base 4 of some expression equals log base 4 of the other expression. Well, again, this is our classic duh scenario. Okay, log of something equals log of something else, so it must be true that those two guys equal each other. Okay, and okay, we call up our local Algebra 1 student, and our Algebra 1 student very quickly tells us that I've got 10 equal 2x, so that x equals 5. Alright. Okay, now, funny thing about logs, though, is remember, the log, whatever this expression is, inside the log is the way I like to say it, that guy's got to be positive. Alright, so if I have this x value that makes either of these parentheses negative, then I got to throw them out. But 5 plugging in there makes a 14, plugging in there, and by no coincidence also makes a 14. So, hey, I feel good about it. Number one, it gave me the same expression, or the same value inside both parentheses, but also it's positive in both cases. So, I feel like that's a good answer. Now, I say that, of course, because as I look at this one, again, I've got log equals log, and so that means that x squared plus 4 has got to be equal to x plus 10. Okay, now I got a square, so I'm thinking I might factor or something like that, so let me smash everything onto one side. X squared minus x, subtract the 10 gives me minus 6 equals 0. Okay, and after a little bit of factoring, I'm going to get an x plus 2 and an x minus 3. So of course that lets me have x equals negative 2 and positive 3. Uh-oh, but wait a minute. If I have a negative coming out of one of these guys, I'm in trouble. So as I plug the negative 2 in there, I get negative 2 squared is 4 plus 4 is 8. Okay, and then negative 2 plus 10, also 8, so negative 2 is good, so I get to keep him. Yay! And then the 3, same thing. 3 squared is 9 plus 4 is 13. 3 plus 10, also 13, so actually I get to keep them both. But just keep in mind, if that happens, you do have to throw out the one that gives you a negative result on the inside. So don't assume just because it's negative it doesn't work, but at the same time, double check your answers just to make sure it doesn't give you something extraneous. Alright, let's do some word problems. Woohoo! Yeah! Hooah! And all that kind of stuff. Anyway, the relationship between the number of decibels and the intensity of a sound is given by this equation here. So, hey, let's start working it out and see what happens. Okay, the number of decibels, well, I want intensities of 1 and 100. So intensity is our I, so all I have to do is plug a 1 and a 100 in for I and work it out 2 different times. So decibels equals 10 log of 1 over 10 to the negative 12. And if we successfully put that in our calculator, we should get out 120 decibels. Alright, for option 2, for 100, well, let's go 10 times log of 100 over 10 to the negative 12. And successfully typing that into our calculator should get us an answer of 140. Alright, so pretty cut and dry from there. Although if you think about that, and basically this is what part B is doing, one sound is 100 times more intense, but how do the decibels compare? Well, we certainly don't get 100 times as many decibels. So basically they're only 20 greater, or if you want something in more of a multiplicative sort of idea, if 100 times greater actually only gives us 1.16 repeating times is great. Okay, so this is basically just stressing that a logarithmic scale or a logarithmic relationship is not linear in nature. Okay, if it was linear, if I multiply one of them by 10, I end up multiplying the other by 10 or by 100 by 100, whatever. But this definitely doesn't play out that way. When we start graphing these things, and I know you're looking forward to that, hopefully the shape of the graph will shed a little more light on exactly why that's the case. But for now, there you go.